Hello student, very good morning to all of you. How are you? I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think yesterday we were discuss about the scheme number 2 where we have seen or we have studied the scheme number 2 step by step by using different reagent and the proper condition, and whatever the reagent, suitable reagent and the condition required in it, that we have described in our previous lecture. Today what we are going to discuss or what we are going to learn, that is the scheme number 3. So here actually in a scheme number 3, let us discuss little bit about that, the previous recap of the previous scheme, which is second. So in that, continuing on the path toward Pinnaic acid with the S configuration at C14, natural or unnatural, the C15 alcohol of 50 was exposed by cleavage of the TB-DPS group. TB-DPS group is nothing but as a protecting group which protect the hydroxyl group, and the full form of that TB-DPS would be tertiary butyl diphenylsilyl, and at this point considerable difficulties were encountered. The first of this was on inability to oxidize 15 to oxidize 15 to the corresponding aldehyde at C15. The situation here was clearly more complex than in the case of polychlorine, since the proximal nitrogen atom in pinnaic acid must emerge eventually as an NH group. This is in contrast to polychlorine, in which the synthetic target mediates the tertiary character of the nitrogen atom at a considerable point. The choice of proper protecting group for the NH group of 15 toward NH group of 15 turned out to be critical if it would be necessary for this group to enable a diverse set of reaction and to be responsive to deprotection in a straightforward way at one of several stages. After many frustrations with various groups, they settled on the trifluoroacetyl derivative to form 16. Deprotection of the TB-DPS group gave 17, which was oxidized to aldehyde 18. We then set out to form the C14 epimer S configuration building block of aldehyde 18, anticipating a synthesis of the R version of pinnaic acid. And for this purpose, they returned to the methylated Meyer's lactamate, deprotection of 8, LiH-MDS, and kinetic quenching 2,6-ditertiary butyl 4-methylphenol gave rise to 19 as the major product. Forward processing of 19 as shown in scheme 3 afforded after careful column chromatography, pure primary alcohol 20, 58%, 2 steps. And let's see the scheme number 3. What does it that we are now discussing over here. Now look at the structure carefully here. I am showing nitrogen atom at this position, 5 membered ring, immediately joined to another 5 membered ring where the side chain which has this group, olefinic group present on that, carbon atom common to that 5 membered ring, and that amine is generally protected by the group that is a Bock benzyloxycarbonyl group, which is a very good protecting group which can protect the amine. And at this point there is a methyl group which I am representing here by Me, and this structure is nothing but as a structure number 8. And now I am adding the reagent A on it. After the addition of reagent A, what could be the reagent A? That we will see shortly after the completion of this structure representation of the scheme number 3. So now when added the reagent number A over here, what do you get? You are going to get here the structure are as shown in figure here. N, there is this Bock is a protecting group, and now here dotted bond indicate that they goes below the plane. Now immediately 5 membered ring, which is other part of the organic compound I am representing here, they remains as it is. Now this carbonyl group here dotted line indicate that that bond is going to break, and here I am showing it means that the bond which is going to form over here, and here is a methyl group which I am showing over here. Now I am putting negative charge at that corner point, where on the other side there will be a lithium which carries positive charge. So as a mechanism point of view, I am showing this in the square bracket, and as we know that mechanism means what? A detailed study of sequence of steps which are involved in the conversion of reactant into product is known as a mechanism. And in other way round, generally we can say mechanism is nothing but as a language of organic chemistry. Those are knowing as a mechanism, they able to understood the chemistry in a better way. So that the mechanism I have shown over here. Now this negative charge is going to attack on that, because this negative charge species is always termed as nucleophile, and which is just like as the water flows from higher level to as a lower level. So it is seeking the electrophilic species, means the species which is electron deficient in nature, and that's why it is attacking on that H plus. And now here I am showing, here is a H plus proton in an inverted comma, that is from B phase. This is from B. There is a phases generally A phase and B phase, from where that hydrogen atoms are coming, that generally showing B phase means from the above side, and beta phase means the hydrogen atom, the incoming group coming from the upper side, and alpha phase means the incoming group approaching from the backside. So that is the generally the sum of the symbol which represent the meaning in the organic chemistry, and that's why it is shown over here. And now look at carefully, I am inverting that arrow. You must stay with your connectivity. Now I am showing this arrow like this, inverting that arrow. After that, what do I get? I am writing here N, that 5-membered ring as it is. Another 5-membered ring immediately attached over there, and there is a Boc is a protecting group. The carbonyl group once again retained, but at this position the methyl group which is goes behind the plane, and because the proton which is coming from the beta phase, and that's why it is shown by thick bond, and you can clearly observe in the structure number 9 we can say here the group which is present, this one, this is the compound which we got. This compound is number is a 19. After this mechanism we could or we would show, we would represent in this manner. Now let me clean this structure, but you should essentially stay in a connectivity. Now I am inverting, I am showing as a arrow like this, where I am adding the reagents B and C together. What would I get, or what would we get? Let's see. We would get the structure number 20 here. This is a structure number 20. And how do that structure number 20 is looks like this. So the side chain which is present here, this is a allylic olefin along with nitrogen atom, which is a nitrogen atom which is protected by Boc. Boc is a suitable protecting group for amines, and that's why it is there. Now the hydrogen atom shown by thick line means that hydrogen atom above the plane. Another one, the methyl group, which I am representing over here, that would be below the plane, and therefore I am representing by dotted lines, dotted bond. And now here will be the hydroxy group, which is free hydroxy group, primary alcoholic group, and that is nothing but as a structure number 20. And the structure number 20, now I am again essentially converting that structure number 20 by doing the multiple steps. I would get the next structure. The next structure would be this one, the 5-membered carbon skeleton or cyclopentane, having the side chain is like this, which I am representing like this. So you can observe carefully. There is a double bond. There is a double bond. After that there will be a methyl group immediately joined with ester group, that is a side chain, where the other group which goes behind the plane, that is a protected primary group. I am mentioning here R could be a different one that we will see later on. Here the hydrogen atom which would be above the plane. Now the group not here like this, but that bond is showing this way. The methyl group which comes above the plane, which is represented as shown in figure, and there is a protected, that hydrogen atom would get replaced by TB-DPS, means tertiary butyl diphenyl silyl, which is a very good protecting group for alcohol, and it is protected over here. Now what would I get? The structure number 21, when R is equal to BOC, BOC. That is the structure number 21. Suppose as a 21 further treated with the reagent D, and after addition of the reagent D, I would get the structure number 22, where R is nothing but as a hydrogen atom. And now remember, when 21 structure, when I am treating with the reagent E, because shortly after completion of this scheme, complete scheme, immediately we are going to discuss about the reagent. What are the reagents we would use during the synthesis? Here just we are representing by the alphabetical letters, that is alpha A, B, C, D, E, F, G, H, I, like this. So here the E reagent, after the addition of E reagent, we would get the structure number 23, and which I am representing over here. So you can see here, this is a 5-membered ring. No, don't show that one. So what is going to happen? Azaspiro moiety must be formed over here, which I am representing here. This is above the plane. Now there is a 5-membered ring which is attached like this. This is a spiro core, means one of the carbon atom shared by 2 rings together, and that type of the organic bicyclic compound are generally referred as azaspiro. Aza means there is a nitrogen atom involved in one of the ring. Here particularly in a 6-membered ring, it is a heterocyclic ring further attached to the 5-membered ring, sharing with 1 electron, and that's why it is a azaspiro framework, which is a very, very important role playing for the synthesis of pinnaic acid, because pinnaic acid containing the azaspiro ring, and which is very, very difficult to make it, but they have made that ring very easily by using these suitable reagents. And now here I am showing there is at 5-membered ring one group which is above the, and that is carbon number 5. Further there is a double bond, here is a methyl group followed by attached ester group, is carbon number 2, 3, 4 and 5, like that. And now here the hydrogen atom which is coming above the plane and other side chain, here the methyl group which coming out of the plane, means above the plane. Then this is a hydroxyl group protected by TBDPS, means tertiary butyl diphenyl silyl, and we got the structure number 23 over here, and which you can observe here carefully how it forms. Now once again I am reverting the arrows, but you must stay with your connectivity. Don't disconnect your connectivity. Now on 23, after the multiple steps, we would get, or they would get, they would have got the structure, and that structure I am representing here. So you can see here NH, then there will be a one group which is above the plane, I am representing like this. And now the 5-membered ring I am showing over here like this. This is a 5-membered ring, that is azaspiro ring, which is shown over here. And after that here is a, not here, there is a protecting TFA, that is a trifluoroacetic acid. Then there will be a one group which is present like this, and it will be this one, then double bond methyl group, then there will be a carbonyl group and OET. So that is a group which is present over there, and this structure is nothing but as a structure number. Before that, the hydrogen atom coming out of the plane. Now the other side chain which remains here, I am representing here, is a methyl group, and after that methyl group there is a aldehyde group attached over there, and in this way we have got aldehyde group, and that structure is nothing but as a structure number 24. That structure after the 24 we have seen up to that 24, and that is a scheme number 3 which is represented over here. Now whatever the reagent and the condition utilized during this reaction, that we are going to discuss right now here. Let us see, up to the 24 we have seen, we got the proper skeleton which is required for the synthesis of the pinnaic acid, and the structure of 1 which we already discussed in our previous lectures. And now here is a scheme number 3, that is the reagents and the conditions. Reagents and conditions which are as follows. Now first reagent they have used would be A, which is LiHMDS, and which was taken about 1.2 equivalent. Then the solvent used THF tetrahydrofuran. The temperature for this is kept as 40 degrees centigrade, and that reaction mixture was stirred about 1.5 hour, and then there is a BHT, and which was taken about 1.2 equivalents, and the temperature kept around minus 78 degrees centigrade, and which was 1.0 hour, that is 82% yield were obtained. Then let us see B reagent, and the B reagent will be LiOH, lithium hydroxide, and the solvent employed THF tetrahydrofuran as well as water H2O. Then temperature is kept around 25 degrees centigrade, and that reaction mixture were stirred about 18 hours. Then the next reagent they have used will be this one, CO2ET, then NET3, that is a triethylamine, followed by THF tetrahydrofuran, and the temperature kept around minus 10 degrees centigrade, and the reaction mixture was stirred about 1 hour. Then added sodium borohydride, that is NaBH4, sodium borohydride, and the methanol MEOH used as a solvent, and temperature is kept around 0 to 25 degrees centigrade, and that reaction mixture stirred near about 1 hour. Overall yield is obtained 58% over 2 steps. And the next reagent used for it is TFA, and that is used in CH2Cl2 dichloromethane, and temperature kept around 25 degrees centigrade, and that reaction mixture was stirred about 1 hour. And the next reagent were used for it is DBU, as we know that DBU, and the temperature is kept around 25 degrees centigrade, and that reaction mixture stirred around 18 hours, and the percentage of yield is obtained about 26% over 2 steps. And here the short form which they have used during this reaction that we are going to see over here. The one which they have used is BHT. BHT is nothing but 2,6 2,6 ditertiary butyl 4-methyl phenol TFA is nothing but trifluoroacetic acid. So alcohol 20 was converted into 21. The S version of the spirocyclization precursor indeed deprotection of the Boc group of 21 followed by treatment of the resultant 22 with DBU provided 23, which is the S epimer of 15 at C14. Progression of 23 as before afforded aldehyde 24, the S epimer of 18 at C14. In summary, they have secured the basis for synthesizing the C14 stereo container of pre-Pinnaic acid building blocks by highly stereoselective sequence. In the following paper, they have demonstrated how this chemistry set the stage for the total synthesis of natural and unnatural Pinnaic acid in a fashion which elucidates their relative and absolute stereochemistry in a rigorous alcohol. So in this way, we have completed the second article which they have described that by Matthew and co-workers. The third title of that, Pinnaic acid total synthesis and proof of stereochemistry of natural and unnatural Pinnaic acid, a remarkable long-range stereochemical effect in the reduction of 17 oxo precursor of the Pinnaic acid, and which is published in a Communications. Once again, it is a very good reputed journal with high impact factor, and which was described by Matthew W. Koroshan, Gunjal Kim and Samuel J. Danesky. And this paper is dedicated to Professor Umerov for his discovery many fascinating natural procedures they have given in that. So I think with this we have studied the Pinnaic acid, that is a asymmetric total synthesis of Pinnaic acid as per as the requirement according to that syllabus. We have completed here the section second over here of the course CCTP-10. In I think with this I hope whatever molecules we have studied in course number CCTP-10, previously known as 450, as per as whatever the requirement is there, we have taken all the syllabus point to point. Here we have completed the course number 450 completely, section first as well as section second. So I hope, I wish you best of luck for your future. And here I take the completion of that. I wish you best luck. Thank you. Have a nice day.